All right, hello there. So today I will be talking about representation of quadratic partial differential equations as partial integral equations or pies, and how we can subsequently test stability in this pi representation using semi-definite programming. In particular, we'll be focusing here on systems of second order 1D quadratic partial differential equations with linear boundary conditions. So for example, consider here Berger's equation with this quadratic nonlinear term with these linear Dirichlet boundary conditions. And more generally, we will be focusing on systems of this form, where we have these nonlinear terms corresponding to products of the state U, as well as its first order spatial derivative. And we are interested in testing global exponential stability of solutions, where we define exponential stability in the standard manner, requiring the norm of the solution to decay exponentially with time. And here we will consistently be using the standard L2 inner product and the associated L2 norm. Now, to test stability of these quadratic PDEs, we will first actually propose a generalization of the SOS, sum of squares, framework for stability analysis to infinite dimensional states U. Once we have generalized this sum of squares framework, we will apply it to actually test stability of our quadratic PDEs. But first, let's look at this SOS frame. So if we consider a finite dimensional system, an ordinary differential equation, we know that we can test stability by looking for a Lyapunov function. So a function v which is positive definite, but which decreases along solutions to the system. Now, to test for existence of such a function, we can use the sum of squares approach. In particular, we can look for a polynomial Lyapunov function, so that we can represent this function in terms of a monomial basis z on our vector u. Now then, if the vector field f here is polynomial as well, the derivative of this function v along solutions to the system will be polynomial, and therefore can also be expressed in terms of this monomial basis z. Now then, to test stability, we need to enforce positivity of the function v and negativity of its temporal derivative, which we do using these sum of squares constraints, requiring both v and its temporal derivative to be of this quadratic form, parameterized by a positive matrix P and a negative semi-definite matrix Q. Moving now to infinite dimensional setting, we note that for a system of this form, we can again test stability by looking for a Lyapunov function, so a function of v which is positive definite, which decreases along solutions to the system. However, if we want to just test existence of a polynomial functional, we first have to consider what a polynomial function on this state U actually looks like. In particular, in the finite dimensional case, we represent these polynomial functions using a basis of monomials on our vector U. So this raises the question of how we actually define such a basis of monomials on our infinite dimensional state U. And once we have such a basis of monomials, how can we actually define polynomials on these infinite dimensional states? And in particular, how can we parameterize a class of sum of squares of polynomials on these infinite dimensional states? So we will be addressing these questions in the following 3 slides, starting with this first question of the monomials on the distributed state U. So how can we define a basis of monomials on our infinite dimensional state U? Well, for this, let's first consider the finite dimensional case, where the vector u here corresponds to these variables u1 up until un. Now, in this case, of course, degree 1 monomials are given by these variables u1 through un themselves. So this is just the vector u. But then the degree 2 monomials are given by all quadratic combinations of these variables. So that is all products ui times uj for I and j ranging from 1 up until n. And we can represent this product using the Kronecker product of the vector u with itself, where we note that this Kronecker product will involve n squared elements. More generally, we define a basis of monomials of degree d in our vector u by taking d Kronecker products of the state u with itself, where we note that this d order monomial will also involve n to the power of n elements. Moving now to the infinite dimensional case, we note that where our finite dimensional vector u here is indexed by this discrete variable I, ranging from 1 up until n, In the infinite dimensional case, the vector u is indexed by a continuous variable s ranging over the domain 0 to 1. So then, just as the monomials of degree 1 in the finite dimensional case are given by all ui for I ranging over 1 up until n, in the infinite dimensional case, we should consider all variables u at s for s ranging over 0 to 1. So this, of course, corresponds just to the state u itself. Similarly, the monomials of degree 2 in the finite dimensional case are given by these products ui times uj for I and j ranging from 1 up until n. So then in the infinite dimensional case, we should consider all products u at s times u at theta for s and theta ranging over the domain 0 to 1. And we can represent this product using the tensor product of the state u with itself, where we define this tensor product at a point s called theta to be just the product of u at s times u at theta. Now note then that where in the finite dimensional case, this Kronecker product will suddenly involve n squared elements, in the infinite dimensional case, this tensor product involves just a single element, but it will be a function of two spatial variables. So that is, the degree here determines the dimension of the function. Similarly, we can define a basis of monomials of degree d in our state u by taking d-ordered tensor product of the state u with itself, where we note that again, this d-ordered tensor product will involve just a single element, but it will be a function of d spatial variables. So in this way, we can define a basis of monomials on our distributed state u, and we refer to these monomials as our distributed monomial basis. Now, the next thing we want to do, of course, is to actually define polynomials using this distributed monomial basis. And for this, consider first just our degree 1 monomial, the vector u itself. Now we note that this degree 1 monomial is a square integrable function, and therefore any bounded linear function on this vector u can be given as the inner product of the vector with another square integrable function a. And we can represent this operation as an integral operator with kernel a acting on the vector u. Similarly, if we consider our degree 2 monomial, we note that this degree 2 monomial is given by another square integrable function, now in two spatial variables. So then any bounded linear function on this degree 2 monomial can be given as the inner product of the monomial with another square integrable function b, now a function of two spatial variables. And we can represent this operation using a double integral operator with kernel b acting on your distributed monomial of degree 2. More generally, we can define any polynomial on our distributed state u here using a bunch of integral operators ck acting on the kth order polynomial, where the kth integral operator ck has a kernel which is a square integrable function of k spatial functions, dimension. So for example, we can define a cubic polynomial of this form, where you see that the operator acting on this cubic monomial here is given by a triple integral operator with this kernel here defined using three variables as theta and eta. Now, of course, these integral operators are linear operators, so that linear combinations of any of these polynomials will be a polynomial as well. But we can actually also show that the product of two distributed polynomials is a distributed polynomial as well. For example, if we consider these linear polynomials here, defined using these integral operators with kernels a and b, then the product of these linear polynomials can be represented using a double integral operator acting on our quadratic monomial here. And in fact, the kernel of this double integral operator is given by the tensor product of the kernels a and b. More generally, for any two kernels a and b, which are functions of k and l variables respectively, we can define the tensor product of the associated integral operators here as another integral operator, where now the kernel is given by the tensor product of the kernels a and b. Note then that this tensor product of the kernels is a function of k plus l variables. And then defining the tensor product of these integral operators in this manner we can show that for any two polynomials, P1 and P2, defined by integral operators C1 and C2, the product of these two polynomials is again a distributed polynomial with integral operator defined by the tensor product of the integral operators C1 and C2. So for example, if we consider the product of this quadratic polynomial P1 and this linear polynomial P2, then the result will be a cubic polynomial where you see that this kernel corresponds to the tensor product of this kernel and this kernel. So in this way, we can define polynomials on our distributed state U using these integral operators. What remains to do then, of course, is to actually parameterize sum of squares polynomials on these distributed states U. And for this, we note that if we take the inner product of our state U with itself, then the result will be a positive definite polynomial. What we can do is we can parameterize this inner product by an integral operator Q, where now this integral operator maps a function in a single variable to another function in a single variable. And in particular, the kernel of this integral operator involves not only the dummy variable eta, but also introduces a new variable s. Similarly, we can take the inner product of the quadratic monomial with itself and parameterize this inner product using another integral operator r, where now this integral operator maps a function on two spatial variables to another function on two spatial variables. More generally, we can consider the inner product of a monomial basis with itself and weigh this inner product using an integral operator p, where each of these blocks, pkl here, maps a function on L spatial variables to a function on K spatial variables. And then crucially, of course, if this integral operator P here is positive semi-definite, then that ensures that the function V here, this polynomial, will be positive semi-definite as well. So for example, if we consider this integral operator R here, what we can do is we can actually take the product of the integral operator with itself and then scale it with a matrix P. Then, if this matrix P here is positive definite, the resulting operator P, the integral operator, will also be positive definite. And as a result, this quadratic polynomial will be positive definite as well. So in this way, we can actually parameterize a cone of positive semi-definite polynomials using positive semi-definite matrices. So at this point then, we have all the tools we need to actually apply this SOS framework to systems involving these infinite dimensional states. What we want to do, of course, is apply the SOS framework to testability of our quadratic partial differential equations. And for this, we first need to represent our quadratic PDE dynamics in terms of these distributed polynomials. However, we note that our SOS framework is defined on these states U that are square integrable, whereas our PDE dynamics are generally defined on a much more narrow domain involving boundary conditions and continuity constraints. For example, if we consider Berger's equation here, we note that our state U at any time t must be an element of this state space X, required to satisfy these Dirichlet boundary conditions. So then in order to represent this system in terms of our distributed monomials, we will actually represent the dynamics in terms of this second order derivative of the state. In particular, we note that using the fundamental theorem of calculus, we can express our PDE state U in terms of its second order derivative using these integral operators, as well as these boundary values of the state. Similarly, we can express the first order derivative of the state in terms of this second order derivative and these two boundary values. Now, of course, by the boundary conditions, these terms here will actually be equal to 0. And therefore, we can express our PDE state U as well as its first order derivative directly in terms of this second order derivative of the state, which we refer to as our fundamental state, and we will call V. Now note then that this map from the fundamental state to our PDE state is defined by these partial integral operators or pi operators T and R. Now substituting this relation then into the PDE, we obtain an equivalent representation of the system as a partial integral equation or a pi, where now this fundamental state V here is free of any boundary conditions or continuity constraints, and where the dynamics are now expressed in terms of these partial integral operators rather than these differential operators. Of course, this is just one simple example of a PDE, but in fact we can show that for any sufficient suitable linear boundary conditions, we can always define partial integral pi operators T and R to express the state U and its first order spatial derivative in terms of this second order derivative of the state. So, if we consider then a quadratic PDE as we presented at the start of the presentation, what we can do is we can define these partial integral operators T and R to express the state and its first order derivative in terms of this second order derivative of the state, and we obtain an equivalent representation of the system in terms of this fundamental state V. Now note here that, for example, this product of T applied to V and R applied to V is in fact a product of polynomials on this distributed state V. And therefore, we can actually express it in terms of this distributed monomial by taking the tensor product of these partial integral operators T and R, as well as T and T and R and R. Finally then, we can take the composition of this multiplier operator A with this pi operator, as well as this multiplier operator B with these pi operators, and express the dynamics very concretely in terms of our second order monomial basis on our fundamental state V, using yet another partial integral operator C. So using this approach for any quadratic partial differential equation with suitable linear boundary conditions, we can define an associated quadratic partial integral equation where now the dynamics are expressed as a distributed polynomial on our fundamental state V. Because in this pi representation, we can then actually apply the SOS framework to test stability. In particular, if we consider a quadratic PDE with the associated quadratic pi representation, then we can parameterize a quadratic sum of squares Lyapunov functional V by a partial integral operator P, as we do over here. Now note that since for any solution U to the PDE, there exists an associated solution V to the partial integral equation, we can represent this Lyapunov function in terms of this fundamental state V. Then, taking the temporal derivative of this function along solutions to the partial integral equation, note that it takes this pseudo-quadratic form defined by this partial integral operator over here. So then using this simple quadratic Lyapunov function, we find that if there exists a positive definite pi operator P, such that this operator here is negative semi-definite, then this ensures that solutions to this PDE are in fact exponentially stable. So let's apply this to some examples, starting with Burger's equation, as we've seen before. And in this case, we add this reaction term parameterized by a variable R. Now, of course, we can define an equivalent partial integral equation representation, where again, we get the same reaction term over here, where solutions are related through these partial integral operators T and R. Now, for the Burger's equation, if we exclude this reaction term here for a moment, it is well known that we can verify stability using this simple quadratic Lyapunov function. And in particular, performing integration by parts and invoking the boundary conditions, we can show that this temporal derivative is given by these two terms, where this second term here drops out, and where this first term can actually be expressed as an inner product spatial derivative of U with itself and a minus sign in front. So this then shows that this Burger's equation without the added reaction term is in fact stable. Now, of course, we would like for the SOS framework to be able to replicate this result. And indeed, if we consider this same Lyapunov function, now expressed in terms of the fundamental state, where we note that T applied to the fundamental state just returns the PDE state U, then we can show that the temporal derivative of this function along solutions to the pi takes this form using these two terms, where again the second term drops out. We can express the first term using the inner product of RV with itself. And here, of course, we note that RV exactly corresponds to our first order spatial derivative of the state, meaning that these two temporal derivatives are indeed identical. So using the SOS framework, we can verify stability of the Burgers equation using this same Lyapunov function. Now then, reintroducing this reaction term R, we note that with the same energy functional, we can actually prove the system to be stable whenever R is smaller than pi squared using the Poincare inequality. Performing bisection on the value of R and using this quadratic Lyapunov function parameterized by an operator P, we can verify stability for any value of R smaller than 9.8696, which is very close to this analytic stability bound. Now, as another example, consider the Quadratic-de Vries equation, where we now have a third-order temporal derivative of the state. So then we can derive an equivalent pi representation of this system using the fundamental state, this third-order derivative of the state. Now note that we've added some quadratic reaction term to the system here, which also appears in our pi representation. And then using the sum of squares approach, we can verify stability in the pi representation for any value of this parameter R smaller than 4.6098. Actually, using this fairly simple Lyapunov function, we can verify stability analytically for any value of R smaller than 4.0017. So clearly, this analytic result is conservative, but it's unclear how accurate our numerical result over here then is. Finally, consider the Kuramoto-Sivashinsky equation, where now we have a fourth-order spatial derivative of the state. Then we can derive an equivalent pi representation, where the fundamental state is given by this fourth-order derivative of the state. And again, we've introduced another quadratic reaction term here, which also appears in our pi representation. And using the SOS approach, we can verify stability whenever this value R is smaller than 0.6500. Whereas using a fixed Lyapunov functional, as in over here, we can verify stability analytically for only R smaller than 0.3608. So clearly, again, this analytic result is conservative, and it's unclear how accurate our numerical result is. So to conclude, we can use this SOS approach to actually test stability of these quadratic PDEs with linear boundary conditions, where we define our distributed polynomials and thus the SOS polynomials using these tensor products of the state V with itself. We can represent our quadratic PDE in terms of these distributed monomials as partial integral equations. And then finally, we can test stability in this pi representation using the sum of squares framework. Now, we've actually made some codes available on CodeOcean, which we use to run the tests presented in these examples. So this is freely available online. And with that, I would like to thank you very much for your attention.